So in this video, I just want to look at an example of how we could find this derivative if we are given the parts of the tangent line. Okay, so we're usually going the other way. We usually want to find the tangent line by finding the derivative. But let's say we have an example where we're told that the tangent line to the graph of f at the point 2, 3 passes through 7, 6. Okay. So we want to find what we would call the derivative at x equals 2, okay, or at the point 2. So we're not told anything about the function here, right? So we're just told that we have this point at 2, 3, okay, and we have this other point at 7, 6, and that the tangent line of the function passes through these points. So again, we really don't know where the function is or what it looks like, but we know that it intersects this line at only this point, right? So maybe it looks something like this. Maybe it's on the other side of the graph or of this line. We're not really sure. But the slope of this line intersecting at that one point will tell us the slope of the function at that point, which is what we call the derivative. Okay, so here it's just as simple as finding the slope of the line. So again, it's really just algebra. So the slope of the line, maybe we call it m, like we typically would. We would do 6 minus 3, the difference in the y values, divided by 7 minus 2, the difference in the x values. So we get 3 over 5. Okay, so the slope of the function at this point is 3/5. Again, the slope at that point, not the output or anything like that. Okay. So let's go back to the diagram and look at how this tangent line works. So I have this one right here. This is for the function x squared again. So if we wanted to find the slope at any point of this function x squared, what we want to do at a specific point, so let's say we want to find it at 1, then what we do is we find the slope of the tangent line at that point. So it's hard to really see how it intersects only at that point, right? But this one, this is what this diagram is showing though. Okay, so at 0, again, that's kind of where it's flattening out. So maybe we would assume that the slope of the tangent line would be 0 because it would be an exact horizontal line once again. And you could show that algebraically. You can show that the line y equals 0 intersects the function f of x equals x squared at exactly one point, which is at 0. Okay. So what about this one right here? It's a little bit harder to imagine here. Okay, and there's nothing giving us the value of the slope on the line on the graph over here. So maybe we look at the secant line, which I've switched over to here. So maybe we look at, okay, well, here's 1. It's hard to get it centered exactly on 1 here. But, you know, we get it pretty close to 1 here. And then maybe we keep bringing that secant line. Oops, I did it backwards. One of these points moves it. One of them moves it inwards. Okay, so what if we look at this point now where we're at 1. There we go. At 1 exactly. And now we move this point inwards. So this is finding the secant line between 2 points. The m right here gives us the slope of that secant line between 2 points. So we're moving it inwards. And what does it look like is happening to the slopes of those lines? Well, it's getting closer and closer to 2. And when we bring it on top of it, it's undefined. But then if we go in from the other side, we still see it's getting closer and closer to 2. So this is giving us the impression that the derivative of x squared at x equals 1 would be 2. Okay. So how can we verify if that's true? Okay. Well, what line has a slope of 2? Well, that would be a something like f of x equals 2x, right? But then we also have to consider the y-intercept of that line. So what's going on here with the y-intercept? Oops, I moved the wrong one again. Okay, it looks like if we put them right over each other so that it's undefined or gets closer to, it looks like it's the y-intercept is getting closer to -1. Okay. So let's try that line out. Let's say that we have f of x equals 2x minus 1. And let's call x squared g of x. And let's see if they intersect only at that point. In other words, is 2x minus 1 the tangent line of x squared at x equals 2? Or I'm sorry, x equals 1, right? We're finding the derivative x equals 1 in that diagram. So if we set these equal to each other, then we get x squared minus 2x plus 1 equals 0. So this is x minus 1 times x minus 1, so x minus 1 squared. Take the square root of both sides, x minus 1 equals 0, so we get x equals 1. So this is indeed the only point where these two functions intersect. So in other words, 2x minus 1 is the tangent line of x squared at x equals 1. And therefore, the slope of that line is the slope of x squared at x equals 1, which is what we call the derivative. So the derivative of g of x at x equals 1 is 2. Okay, so how we would write that, the notation for the derivative. So let me just write the notation here. There's different types of notation. So there's what's called the Lagrange, Lagrangian notation, I think is what we call it. So for g, since we call g x squared, this would be g prime of x, which is like a little apostrophe on the g. And specifically here, we're looking at the point 1. So we'd put that point in here and we would say g prime of 1 is equal to 2, right? The slope of the tangent line at the point x equals 1 is 2, or the derivative of the point, the derivative at x equals 1 is 2. So this makes more sense when we only have a single variable. If we have multiple variables, then we need to specify which variable we're looking at the derivative with respect to, right? So when we open it up to multivariable calculus, which would be the focus of Math Tools 3, we might take the derivative with respect to x or y or t or whatever. When we just have one variable, the prime notation is unambiguous, so we might just leave it like that. So this one is it's nice because it is compact, succinct, easy to write. The Leibniz notation is usually kind of preferred because it gives us more of a physical sense of what's happening. So here we would say that dy divided by dx. Now, how you write this is really dependent on what you call your function. In this case, it would make more sense to call this d dx of g of 2, or sometimes this is written as dg over d of x of 2, or the g part is not used and we just say dy of dx of 2. Or sorry, these are all of 1. I keep getting the 1 and 2 mixed up. But we're finding the derivative at 1, and that's equal to 2. Okay. So these are all kind of used interchangeably. The point is that you're taking the derivative of g with respect to x, or the derivative of y with respect to x. Again, y and g are kind of interchangeable. And this is telling you at what point you're doing it at, right? So maybe you're not doing it at a point, maybe you're just doing it at a general x, and then you just have an x there. So the Leibniz notation, the advantage is that it kind of gives us a physical sense of what's happening. Dy over dx, what this means is that this is like looking at a very small change in y over a very small change in x. And what I mean by very small change is an infinitesimal change. Okay. So these are what's called infinitesimals. Let me write that out. Infinitesimals. Okay. Which means, infinity means that it's, unbound. It's unboundedly large, right? Like it's just so large that there's no bound on it. So this is kind of going the other way, but at 0. So this is saying it's so close to 0, it's almost indistinguishable from 0. So in other words, it's like the limit as you go to 0. So of course we know the quantity 0 over 0 is indeterminate. So this is kind of distinguishing it from that, we're not exactly going to 0, but we're looking at an infinitesimal change in y as you do an infinitesimal change in x. Okay. So it's often cautioned with this notation that, of course it's a fraction, right? But it's not going to follow exactly the same fraction rules that we always will see, but it does kind of follow a lot of them. So that's why this notation is used. But, just take a little bit of caution with it because it's not exactly a fraction when you're dealing with infinitesimals like this. Because you're dangerously close to dividing by 0, right? So weird things can happen here, but this notation is chosen for a reason, which is that it does often follow a lot of those same rules as decimals. So we'll kind of move interchangeably between the prime notation and the fractional notation. The prime notation, again, is just kind of easier to write, whereas the fractional notation kind of gives us a better sense of what's physically happening. And in some cases, it's a lot more convenient to use this notation because, again, it does follow some of those fractional rules. So we'll see some simplification that we would expect, based on those fraction rules. And then when we get to the integral calculus part, the dx's and the dy's are used everywhere, so it's good to be used to them for that reason as well. And then real quick, I just wanted to mention that Newton actually had a different notation. It's not really used much today. The textbook I'm referencing says it's used in physics, but I can't confirm nor deny that. I never took a calculus-based physics course personally. But the Newton notation was that he would write a dot over the function. Okay, so you'd have a dot over g of x. So in this case, dot of g of 1. Okay. So again, that's kind of fallen out of style. I've never really seen this notation used in practice. But just know it exists. If you ever are curious enough to go read Newton's original work, you'll see that there. But we'll stick with one of these two.